Hello, everyone. We are honored to present our paper, Augmented Reality Art Museum Mobile Guide for Enhancing User Experience. Today, we will discuss how our AR system optimizes indoor navigation and enriches the visitor's journey within the museum. The indoor navigation system developed in this study effectively guides visitors to specific exhibit locations. Upon entering the museum, visitors simply open the application and select their preferred artworks or follow our curated recommendations. The system then generates a virtual route leading them directly to their destination, ensuring a seamless experience. To begin, the visitor selects an artwork of interest and performs the initial localization. Once the position is established, the visitor follows the virtual trajectory on the screen to reach the exhibit, and upon arrival, can utilize the scanning feature to access detailed commentary. The featured artworks section highlights key exhibits recommended by the museum. Once a visitor selects a piece of interest, they can access detailed information along with its precise location. Upon entering navigation mode, an initial localization process is required, achieved by panning the map to indicate the current position and clicking to confirm the coordinates. The panel on the far left illustrates the calibration anchor point. Once the camera detects this reference marker, the system automatically recalibrates and updates the user's real-time position. Visitors then follow the AR overlay to reach the exhibit, and on-screen icons will signal their arrival at the specific artwork. Upon arriving at the designated artwork, visitors can seamlessly transition to the scanning module. By aligning the smartphone camera with the exhibit, the system retrieves and displays essential metadata, textual descriptions, and integrated audio commentary, providing a comprehensive, multi-sensory experience. This flowchart illustrates the overall structure of our proposed system. The application supports both iOS and Android devices. When launched, the system automatically detects the operating system and activates the corresponding SDK ARKit for iOS and ARCore for Android. While both SDKs serve the same navigation purpose, ARKit demonstrated higher accuracy compared to ARCore. Implementing reliable navigation within a museum requires overcoming the inherent limitations of GPS technology in enclosed spaces. GPS signals are significantly obstructed by the building's architectural structure, resulting in signal strength insufficient for precise positioning. Consequently, it is essential to leverage alternative technical frameworks to achieve accurate indoor navigation. The AR World Map feature within Apple's ARKit is a cornerstone of our implementation. By scanning the physical environment, developers can anchor virtual objects and save these spatial maps. When the application is relaunched, ARKit recognizes the surroundings and synchronizes them with the saved data, ensuring that virtual navigational elements remain stable and consistent. For our research, we utilized Unity's AR Foundation, which dynamically interfaces with ARCore on Android and ARKit on iOS. This system leverages advanced device tracking by fusing visual data from the camera with motion data from the accelerometer and gyroscope, allowing us to precisely calculate the user's movement direction and distance for accurate indoor navigation. To establish a foundation for high-precision navigation, we meticulously reconstructed the entire interior of the museum within Unity. This digital replica serves as the spatial framework for all subsequent navigational logic. Regarding the navigational routes, we employed Unity's native pathfinding features utilizing the A-star algorithm. However, standard algorithms often generate paths that hug walls too closely, potentially leading visitors into obstacles. To resolve this, we introduced a specific offset from the walls, reducing errors and ensuring visitors can follow the guided path safely. This figure shows the data collected from smartphones, including height and atmospheric pressure values across each floor. As shown in Figure A, height estimation using GPS signals reveals no significant differences across the 4 floors, meaning GPS alone is insufficient for floor detection. However, figures B and C show that atmospheric pressure values have clear and significant differences between each floor, both on sunny and rainy days. This confirms that atmospheric pressure is a reliable indicator for determining which floor a visitor is on. This figure shows our calibration point setup locations. Currently, 2 calibration points are established on the first floor. When visitors use the navigation system over extended distances, sensors may experience accumulated drift, compromising guidance accuracy. To address this, calibration points are placed near prominent environmental features and near the elevator and stairs, allowing visitors to recalibrate their position in real time. Once the indoor navigation system guides a visitor to their chosen exhibit, they can seamlessly transition to the scanning feature, providing instant access to audio commentary and textual descriptions. To verify horizontal movement accuracy, we walked 3 random paths and returned to the starting position each time. The relative offset distances were less than 7 centimeters, demonstrating that our system can accurately estimate a visitor's indoor position even over extended distances. For vertical movement accuracy, our system uses the phone's built-in barometer to detect floor changes at 1 Hz. We conducted 24 floor change trials covering elevator and stair usage in both directions. The system failed to detect 2 cases, resulting in an accuracy rate of 91%. Visitors can reinitialize their position at any time, compensating for any missed floor detection. To further evaluate navigation accuracy, we tested 4 artworks across the first and second floors, with each tested 7 times for a total of 28 trials. The results show a navigation accuracy rate of 100%, demonstrating the reliability of our AR indoor navigation system. For our first case study, 93 student visitors were invited to participate. The curator selected 25 artworks and organized them into 5 themed routes, each consisting of 5 artworks across multiple floors. Each participant was randomly assigned 1 route with a fixed visiting order, and upon completion, a questionnaire automatically appeared within the application. The questionnaire evaluated usability, navigation clarity, information comprehension, convenience, emotional experience, positioning accuracy, and knowledge acquisition. Responses were rated on a 4-level scale from strongly disagree to strongly agree. The results clearly indicate a positive evaluation, demonstrating the feasibility of deploying the system in the art museum environment. In addition, a survey targeting the general public was conducted. These participants voluntarily downloaded the application at the museum entrance. Unlike the student survey, this questionnaire used a 5-level scale, adding an undecided option. The system also received positive feedback from general public visitors, further validating its effectiveness across different user groups. To comprehensively evaluate performance, we defined 4 dimensions: educational value, usefulness, enjoyment, and ease of use. Educational value and usefulness confirmed that visitors found the system effective in providing artwork information and supporting exploration. Enjoyment received the lowest score, as 47% of visitors felt somewhat tense during use due to difficulties in initial positioning. Nevertheless, over half still enjoyed the experience. Ease of use results confirmed that visitors found the system made their visit easier and more convenient. For the second case study, 35 student visitors were invited to participate. The experiment focused on 3 artworks displayed within a single gallery room, with a mandatory visiting route. Upon completing the route, participants were given a paper questionnaire to collect their feedback. The questionnaire was designed to evaluate visitors' experience across various tour modes. In addition to the standard questions, a supplementary question was included asking participants to rate their overall experience with 4 different guide modes, using a 5-level scale ranging from poor to superior. This allowed for a more detailed comparison across the different tour modes. As shown in figure, the AR app achieved the highest score, followed by the guided tour in second place. The guided tour allows direct interaction but is limited by time and personnel constraints. HoloLens 2 offers an immersive experience, but its operational complexity resulted in only a slightly better score than the brochure tour, which ranked last due to limited information. Our AR app achieved the highest rating thanks to its convenience. Visitors can simply scan exhibits using their own smartphones, with no time or staffing limitations. The survey confirms that the AR app outperforms the other 3 methods across all dimensions, with HoloLens 2 ranking second overall. This demonstrates that visitors appreciate the effectiveness of integrating technology into museum tours, suggesting that AR, VR, and MR in museum environments represent a growing future trend. In conclusion, the indoor navigation system developed in this study has been successfully applied in the art museum. By combining visual registration and atmospheric pressure sensing, the system achieves precise and reliable multi-floor navigation. According to user feedback, 81% of visitors confirmed the system effectively guided them to their desired exhibits. AR tours outperformed both manual guidance and brochure-based exploration, successfully introducing a new and effective way for visitors to explore the art museum. Thanks for your attention.